Hey folks, so welcome to session 8 of high performance LLMs from first principles. So as always, the goal is to achieve high performance on LLMs. And this week we're going to do actually a variety of things. So we're going to answer some questions that I received between sessions. I thought were all really, really good. Then we're going to actually do something funny, which is implement inefficient inference. So I think one thing I've heard a lot from people is like, why is LLM inference so different from LLM training? So I want to just implement it inefficiently first so people can see why the machinery we've built for training is really ill-suited for inference. And then that means next week we're going to have to do efficient inference, and if there are any more questions between then and now, hopefully we'll be able to take those on. Cool. So again, programming, predicting, profiling, and please just like hop in with questions. So the first thing that really stood out from our comments between classes is we covered model-flop utilization, but actually we didn't really call it model-flop utilization. So let's just make sure we say exactly what that is. And we make sure we understand. So we observed the total model flops was 6 times batching tokens times the number of parameters. We were able to count how many device seconds we spent on each step. So that was the per step time times the device count typically. And then we were able to compute the model flops per device per second. So that's total model flops over total device seconds. And then critically, something we actually didn't really do carefully was calculate a model flop utilization. So what that means is model flops per device per second over peak flops per device per second. There are actually a lot of other ways of calculating it. And in this particular case, I think for some of the numbers we were seeing last week, it was 189 teraflops per second per device in 3. Our peak teraflops per second per device is 275. So our model flop utilization is 68.7%. So this is the fraction of the theoretically achievable performance that we're actually achieving. And you might discover in profiling that the number of flops in the profile, which is typically counted by counting how often the chip is active, doesn't match the model flop utilization. And we'll see, like that. There's a good reason for that, and I'll show a simple example in this session. I think it's pretty confusing. Cool. So, any questions on model flop utilization? Awesome.
How much is it worth looking at 100 minus that and saying, okay, of those missing 31.3%, how much is that achievable, and what's causing all of those different missing unused flops?
Yeah, I mean, first of all, actually 68.7% is incredibly, incredibly high. And it's always worth kind of like pushing a little bit further. It's just about, it ends up becoming a practical matter of how much are we able to drive this higher versus how much that engineering cost is. And in some problems, we'll see we are limited by other factors. So we can look at this one actually. I'll look at one on the next slide. And it is something where we actually, like, for example, we know what the problem is. And actually, we've seen other runs that do fix or improve it. So it's always like, there's no like perfect number. It's always a matter of understanding what the bottlenecks are and seeing if there are ways to get past them. Great question. So concretely looking at an XProf. Oh, Ryan.
Sorry, I have a quick question about the total model flops. So for this 6 multiply batching token multiply number of parameters, in general, do you think this is still the appropriate formulations for the LLM models, or should we calculate layer by layer or other formula? Yeah.
I mean, calculating layer by layer is a little bit better, right?
Okay.
And especially with mixture of experts, which we'll talk about later in the session a little bit as well. That there it's a little bit more accurate. So okay. This is just meant as an approximation.
Okay, thank you.
Great question. Okay, so MFU, there was a question to see a good training XProf. So this is actually from the one that was getting 69% earlier. So there are a lot of different things we can see. We can definitely poke around in this XProf. Unfortunately, only Googlers will be able to see it. But if we look at that XProf, and I think I actually will just pull it up and just screen share into it. The easiest way to look at it is if we look at the HLO op profile, which is our breakdown of time. And what it's telling us is that we're spending 77% of our time getting 89% of flop activity, doing what's called convolution fusions, or just like a fancy way of just saying doing matrix math. And then you can go through the rest of these and see what is happening and how long it's taking. And we can see about 15% of our time, 15.6% of our time, is being taken up on the all gathers and the all reduced scatter fusions, which are two collective communication ops, the cross-chip communications that we actually learned a little bit about hiding. So this particular XProf, if we turned on the right flags, we could do like 5 or 10% faster by getting rid of this all gather. If we do look at what's happening here, you'll see the all gather is taking 512 by 8192 shards. You see this on the left. It's a little bit hard. When I put mouse over, it goes away. But we're taking the 512 by 8192 shards. Remember, there are 4 chips, and all gathering to turning it into a 2048 by 8192 tensor on each chip. So that's the all gather. That's what we expect for this profile, which is a fully sharded data parallelism profile. We can probably see something similar for the reduced scatters. Yeah, so you can see the reduced scatter is similar. It's taking a gradient, which is 8192 by 2048, and then reduce scattering it. So they're being one shard is ending up on each chip, and that shard is 8192 by 512. Cool. So that's what we see in kind of a good profile. Anything else people would like to see in a healthy profile? Cool. So fast flash attention. So I think there's been actually a lot of questions about flash attention. Number one topic for questions. And I think the flash attention actually is a little bit complicated. So before we think about flash attention, let's just think about a softmax. So the problem we're specifically going to think about is taking the softmax of A times B. And if you don't remember what a softmax is, don't worry. We're just going to program that up in Python, and we'll show 2 different ways of programming this and think about which will be faster when. To present something else. Okay, cool. Can folks see my terminal okay? I know that this is frequently somewhat hard to see.
Yes.
Thank you. So we haven't actually programmed a softmax, but we have A and B. And what I'm going to do is just do a simple softmax, and we'll take A and B. And the way this will work is XA will be math.exp. So we aren't going to worry too much about performance for each element in the softmax. This is going to be for x in underscore a. And then we're going to denominator is going to be the sum of XA. And then our output is we're going to do for I in len A. So output equals 0. And then we're going to just show kind of the naive way of calculating a softmax. And that is we're going to do output plus equals x AI. Perfect. And then we'll do return output over denominator. Oops, I have to multiply by BI here. So what this is doing a weighted sum of the B's based on how big their corresponding A is. So if we print out a simple softmax now of A comma B, that should give us simple softmax. Perfect. That should now give us the kind of the data we expect. So it's saying that this is about 3. And the reason for that, again, is because this 30, this entry for the one that corresponds to 3, is much larger than the ones that correspond to the 2 and the 1. So the softmax is saying we put all the way onto the 3, and we get something that's almost a 3. And just for the sake of argument, we'll put a 50 here, and this will take 1.0. So actually, attention is not much more complicated than just being a softmax. So I think if we can understand what this, kind of how the softmax works, we'll be in good shape for attention. And kind of what's the interesting thing about this is, remember that analysis that we used to do in prior sessions where we were thinking about the system diagram? Well, what's happening here is actually if we imagine that the tensors are bigger than what fits in the SRAM, they have to cross to HBM. And then if we look at the code we're writing, this code is going to take one read and write from HBM. This is going to take a second read and write from HBM. This is going to take 2 reads and 1 write from HBM. And it's going to take actually, this is a small thing. So this is going to take, this is 2 reads from HBM. Output is just a single number. So it's just 2 reads. So the whole thing is going to take 4 passes to and from HBM. 5, 1, 2, 3, 4, 5. So this algorithm takes 5 passes back and forth from HBM. So before we go any further, I just want to make sure people understand this. Are people comfortable kind of with the normal way of calculating a softmax, which is kind of the core of attention? Any questions on softmax? Cool. Let's just do another softmax implementation, which is a little bit trickier. So we're going to have streaming softmax. And what we're going to do is actually just a little bit different. So we're going to get rid of these because we don't want to do those. And what we're going to instead do is, as we go, we're going to do exp A equals AI. So math.exp AI. And then sum denominator. And then raw output goes here. And what we'll do is output equals exp A times BI. So now this is taking 1 read. This is taking 1 more read from HBM. Raw output is no longer normalized because we actually don't yet know the denominator. And then we'll say sum denominator equals exp A. So we'll put sum denominator here, and this will be now raw output over sum denominator. And we should probably just print that this actually is computing the softmax we want. So I'll now output both of them, and they both, in fact, compute a softmax. But kind of the critical observation is that this one now takes 2 passes from HBM, while the first one took 5. So we'll catch this to flash attention in just 1 second. But anyone have a kind of a different any questions about these 2 kind of competing algorithms on softmax? Cool. No questions, but hope people are following. So when we think about flash attention, that's really like all flash attention is doing, is really fundamentally that trick. So to sound it out, what softmax is doing is it's creating this matrix, an intermediate matrix. So in our case, we were calling it A. Instead of being very big, sequence length by sequence length, which is very, very large. And instead of doing the naive thing, which is first computing the softmax of it and then multiplying it by V, which is this matrix that we're multiplying it by, all flash attention is saying is, oh, actually, I don't want to first form this weight matrix W softmax and then multiply. I'm going to just do the same trick we saw. So we're going to do softmax we're going to take the exponential, we're going to multiply, we're going to keep track of the denominators as we go, and then we're going to normalize at the end. So this is called an online softmax, and that's the heart of all that's happening in flash attention. I don't want to like at all give the impression though that flash attention is at all simple. So I'm going to just show one really, really easy mistake to make, which we've already made in this example, and kind of a simple way to fix it. So one thing that can easily go wrong when doing the softmaxes is if you have a big input. In this case, A was 1,000. We now get an error, basically because I think it's going to be something like import math.exp of 1,000 just throws an exception. There's not a number big enough in Python to represent that. So I mean, obviously we could set the thing up to be positive infinity instead of an exception, but that wouldn't be good, right? We wouldn't be able to measure this. So there is kind of a canonical trick here, which is you take the max of A, and that would be call it max A, and we subtract that out here. So I'm going to do X minus max A. And now actually the simple softmax that we just patched will work. So it does indeed get the correct answer, which is 1.0. And the streaming softmax will continue to produce an error, right? Because it is naively computing this, math.exp A, and that's going to explode. So there are like a few more tricks required to make this strategy work in practice. But just to highlight it, all that we're doing is exploiting the structure and replacing the softmax with a streaming softmax in flash attention. Another interesting thing is we were just earlier talking about model flops not necessarily being the same as the hardware flops. So this is a very simple example. We've added additional work into this computation. We've replaced math.x with math.x minus max A. That has added a flop actually to that step, but it's probably worth it because we want to get the right answer instead of the wrong answer, and subtracting out max A increases the chance of us getting in practice the right answer. Cool. So unless there are any questions here, I'm going to hop on to the next thing. Cool. So also number of interesting questions about mixture of experts models. So these are really, really important. We're seeing, I think, a lot of frontier models go to mixture of experts. So mixture of experts is actually almost exactly the same as a dense LLM. The only difference is that the feed forward is, let me just present the Chrome tab so we can see it a little bit better, is that the feed forward, there are n feed forwards. So in this case, we've shown them in the blue boxes, and each token goes through a subset K of them. So the case where it is just literally a dense LLM is if n equals K. Alternatively, you can think n and K are both 1, or they can both be 3. It doesn't matter. This is just a dense LLM. Every token goes through every expert. So the reason, like the sounding out more completely, like Mixtral 8x22b is like as an example MOE. There are lots of them. It has 141 billion total parameters, but critically only 39 billion are active for a single token. So that's which actually corresponds to 2 out of 8 experts. So the number of flops per token is equivalent to a 39 billion parameter model, as opposed to being a 141 billion parameter model. And the reason people do a mixture of experts, the whole reason for the mixture of expert idea, is that there's a hope that an 8x22b Mixtral is smarter than a dense model with 39 billion parameters, but we think that the inference cost is going to be close to a dense model with 39 billion parameters. And then we definitely expect Mixtral to not be as smart as a dense model with 141 billion parameters, right? That would be, instead of having to make the choice of what expert you go through, every token goes through every expert. That'd be a smarter model. So the trade-off and everything that the heart of what's going on in the MOE is setting n greater than K requires more communication. It also requires more memory pressure than n equals K. It has the same number of flops, and it becomes an empirical question of whether we're able to get the communications we've added in a mixture of experts to be worth it or not worth it when we look at that, when we look at the end performance, the whole wall clock time of the system, at the same level of intelligence, is it cheaper to have a mixture of experts than paying with more communication pressure but fewer flops? Cool. And then I think that we're seeing a lot of companies are obviously GPT-4 has been reported in the press to be a mixture of experts. Gemini has been reported as a mixture of experts. So lots of mixture of experts on people's minds. So I think it very likely a big part of our future. Any questions on mixture of experts? Cool. Maybe one last thing on mixture of experts. We haven't yet seen them for diffusion, but they'll probably be good for diffusion for the same reasons they're attractive for inference, for LLMs. Okay. So the next question I really hear the most from folks is, why isn't LLM training the same as LLM inference? So I think that this is like really something to think about and really make sure you understand the LLM. So LLM training is of this form that we've highlighting here. So input might be the begin token, then so long and thanks for, and the output is supposed to be so long and thanks for. And that's actually really a fantastic formulation for helping LLMs learn. But at inference time, the need is pretty different. So at inference time, we might start with some prompt. So it might be begin, so long, and we want the output to be thanks and for. But if the neural net makes the choice to make the output I, so now the completion so far is begin, so long, and I, you no longer expect to see the token for. I4 would be kind of like a weird output. So maybe the correct completion would be something like so long and I think you, right? So something else would be the appropriate completion for LLM inference once it's made one token. And really, really critically, what all LLMs are doing is saying, given this prefix, so what is the probability of distribution on the next token? So that's not actually choosing the next token. The LLM gives an opinion on what the next token should be, and then it repeatedly does that. We just have to specify what we choose as the next token, and that allows us to like run LLM inference. So we'll see in a second why that's like so different from what's happening during training. And what I'm going to do, I'm going to try to show this to folks in two different ways. First, I'm going to just show what we're actually doing in LLM training, or trying to apply LLM training to LLM inference. And then we're going to build an inference engine just using the primitives we built in LLM training, and we'll kind of see how it's a little bit goofy. So hopping over here. So this is class start. So what I've done here is I took an LLM. I kept basically all of our code. I kept all of our model definition. And what I've done is I have added a checkpoint that I saved. So we have some kind of like barely trained LLM here. And then I've taken a single input example, and I've run model.apply. I've chosen the most likely output tokens, and now I've visualized them. So I'm going to actually start by showing what this means. So what this is really doing, I'm going to just run this model on our screen, is not going to be actually easy for a human to interpret. It's kind of a really weird thing to be doing. But we're going to print both the input string that we were given, so that's example text 0, the first input string, and then we're going to print out the proposed output string. So this is the string that we output when we ran the neural net, the most likely completion. And something really, really important is it doesn't actually intuitively make sense as a human trying to interpret these answers, because this is fundamentally a training task. It's actually a lot easier for humans typically to think about inference. So we'll take one more second to take a look at this. So this is showing what our guess was at each point, and it's saying the shutdown was aimed at creating efficiency at the plant. Okay, whatever, something at cellulose paste, and this is saying after n tokens in the training input, here is our guess on what our proposed output would be. And it's kind of a hard thing to say because we're guessing E, but actually, like this stuff to the left isn't what the neural net is seeing. The neural net was guessing E after seeing the input prompt up to the next token. So to make that just a little bit easier, I've written us a little utility to just intertwine these two so we can see for each prefix what guess was the neural net making. So hopefully that prefix, that view will be a little bit easier for folks to follow, to understand kind of what the difference is between LLM training and LLM inference. So now we have a real model, just a little bit slower, unfortunately, because I'm like restoring a real model and everything. So a little inconvenient. Cool. So now what we are seeing actually is on the left. So this don't mind the B. This is a byte string. We have a map from what the prefix is to the guess the neural net makes. So the neural net actually, for the empty string, so just before we start, we're going to guess the letter T, which seems like a pretty good guess, actually, right? That's the first character. Conditional on the first letter being T, we're going to guess lowercase h. Also good. By the way, capitalization is good. Conditional on uppercase T, lowercase h is the first two characters. We're going to guess in the second position will be E, and then conditional on THE, we're going to guess space. So one thing that I just want to highlight is the neural net is adapting. So if the prefix is TEH space, the neural net wants to guess C. It's a kind of a totally plausible choice, lowercase c. But once you tell it that that position was actually an S, it will make another plausible choice. It will continue. So ST sounds plausible. And then, okay, SH, it will guess O. So this view is showing what's really happening during training. And it's the same, actually, if these tokens on this diagonal actually match these tokens, but I hopefully in this formulation, folks are able to read what's actually happening. So I don't want to hold here for a few questions. Are people able to just kind of see what's happening here? Thoughts on how our neural net is doing? Cool. So I sort of maybe highlight a couple. Like some of these completions are a little bit weird to me. Like the shut D. I don't think E is going to be a terribly likely outcome. And then the shut GO. I don't think N is terribly likely. So I think there's a little bit more work we can do to make this a little bit more, these completions just a little bit more plausible. Cool. But no questions about this representation? Everyone feels comfortable with what's happening during training? Cool. So we're going to actually jump into now building, Now we're going to actually like build something that does inference. So to remind ourselves what's happening is in this particular previous example, this is the problem that we're solving during training, but there was no way to talk to this neural net, right? It was just doing completion. So to get an experience where the neural net is like you're talking to it at all, you need to have auto regression. So where the neural net has to make the choice. So it has to decide that, okay, after TH space, the next token is C. And then based on that C, we make that choice, and then we feed that forward. So that's what I'm going to do here is we're just going to talk to the neural net. So I'm going to start by text equals np.0. So we're going to make an input of length 0. And then we're just going to, like num tokens, we're just like 10, doesn't matter, for I in range num tokens. We're going to talk to the model. So it's going to be the new text. So the new, we want to just grab from that starting setup, we want to grab a model.apply if we can find it. All right, perfect. So we're just going to do model.apply. So this will give us logits. So critically, the neural net is saying for this neural net is saying, here is my probability distribution. Then we have to choose next tokens. And that we're going to do, there are a lot of ways we could do this, and they all make sense in different contexts. But we're going to do it by taking argmax of logits, axis equals 2. So this thing is distributed as batch, sequence, vocab. So vocab in this case, remember, is going to be 256 because there are 256 ASCII characters. And we're basically going to say, hey, what's our favorite? What is your favorite ASCII character for this situation? So that's going to be new tokens. And then we have to write back to the text. So it's going to be text of 0 because our batch is 0. And then we're going to do I plus 1. So the next token is going to be set to be new tokens 0 I. Just trying to think if we have to. No, should be good. So if we run this should output something. But it's going to be outputting in machine language, right? It's going to be this is going to be in ASCII. So we have to get out of ASCII. So output string. I'm going to just run it just so we can see what happens. But while we wait, output string equals s for I in range num tokens. We have to take each token and detokenize it. So that's the output string plus equals, and then the car of text 0 I. Okay, and then we should be able to print output string. And this is going to be, now we're going to have done inference. Oops, ran the wrong code. Class pretend inference is training. Cool. And I'm just going to throw in a breakpoint so we can just poke around as things go. So this is using the machinery we already built for training and just applying it to inference. And we should be able to talk to the neural net, but one of the keys that we're going to see is this is actually a very, very inefficient and a very, very expensive way of talking to the neural net. So here we want to text here. And the reason that this is so expensive is we're recomputing. So batch is 1 here. So we're modeled on applying for every single token in that sequence. But we're only actually ever consuming new tokens I. But we have to do the model.apply for all of the tokens because it depends on the computing the nth token depends on all the previous tokens. So what we're seeing here is we're printing text, so 084. And then I'm going to just type in CHR of 84. I hope that's right. Yeah, it's saying that that's T. So the neural net is saying that if you give it the empty character to start, it will guess uppercase T. And if we just keep going, we can just see what the neural net hallucinates the whole way. So these first 3 characters are ones we already knew because the neural net always guessed these 3 in the first 3 positions. We already saw that. And since it's guessing what actually happened, it's always going to guess the same thing. And then we know the next one should be a space. So I'm going to hit C, CHR 32. Okay, should be a space. Now the next one should be a C. Right, so we already saw that. CHR 99 should be a C. And now we have no idea what's going to happen. Now the neural net's just going to do whatever it feels like. So I'm going to actually just continue a few times because I don't want to decode all of these. And hopefully our handy dandy script will decode. So the compa. Seems good so far. I'll run this again with maybe a slightly longer number of tokens. The neural net's going to be pretty silly, but we can try 30, see what happens. Cool. While this runs, any questions on what's happening to us here? Cool. I mean, everyone seems very happy or very confused. Would love to just maybe get some sense of where people are and what's on people's mind.
I have a question. When do we stop? Instead of set the longest sequences, is there like any other criteria?
Oh, that's a great question. So you're saying when decoding to you, how do you know you're done?
Exactly. Yeah.
Okay, so the way that works, and we haven't shown it yet, is we have like a beginning token. And in this particular context, actually this neural net doesn't know how to stop, which actually was normal for earlier neural nets. But normally what you do is you add an end of sentence token at the end of the documents. And so the neural net learns to predict the end of sentence token. So if you decode an end of sentence token, you stop the decoding there. So again, the end of sentence token is typically how people detect that they're done. Though there are other ways as well, because the more heuristic ways, the end of sentence is the best way of doing it. And this particular neural net was not trained with end of sentence tokens, though you could guess it would be done if it ever outputs a 0 token during decoding. That would be a sign it would be done. Great question,
Gotcha.
you.
Yeah.
Any more questions? Okay. So I just want to show why this is such a terribly inefficient way of doing things. And then next week, we can implement it just a little bit more efficiently. So I have the breakpoint here. And the thing I want to show us all is logits. So the logits are shaped as 1 by 128 by 256. So we had to process, because our 128 is our sequence length. We had to process 128 tokens just to generate one output token. And then each time we do this, we're going to process another 128 tokens to generate one output token. So the reason inference is different from training, what we're doing right now is the forwards pass of training. And the reason for LLMs, inference is so different from training, is because the forwards pass of training is a really inefficient way of doing inference. And that's not true for all models. That's just true for LLMs and typically other text models. For many other machine learning models, actually the forwards pass of inference really is similar to the forwards pass. The inference is really similar to the forwards pass of training, and they really are the same. So again, it's because of this numpy.argmax, it's because we are making the choice for out of the possible tokens, which token to choose. And we have to make that choice for the model, and the model can only proceed once it's computed the logits and sent back the logits. So that's what's necessary during inference. While during training, we know all of the text in advance. We know all of the prefixes in advance. So we're able to save ourselves that trouble. So again, here we've made an inference engine, actually. We are able to talk to this neural net, but it is incredibly, incredibly inefficient. Again, for taking basically sequence length times too long. So we're paying, again, instead of to generate sequence tokens, instead of taking of order sequence time, it takes of order sequence squared time. So incredibly, incredibly inefficient, but also very, very simple. Cool. Well, that's all I had this time, actually. Without questions, it went a lot faster than I expected. Next time we'll do efficient inference. So we'll just get to the point where we're processing each token separately, and we aren't paying this quadratic penalty. Cool. Any last questions? Cool. Have a good one, folks.